So we resume now, and the next speaker is Nicolas Billerey from Université Clermont-Auvergne. The title of his talk is on Darmon's program for the generalized Fermat equation of signature RRP.
Okay, so thank you, Loic, for the introduction, and of course, thank you to the organizers for inviting me. I am really pleased to talk at this nice conference. So today I'm going to speak about a joint work with Emin Chen, Luis Diolefé, and Nuno Freitas on Fermat equation of signature RRP. So there will be three parts in my talk. First, I will recall some known facts about the modular methods, so the main step of the modular method, and I will focus on the case of Fermat's law theorem for this part. Then I will discuss some extension of Darmon's program, which is already a generalization of the modular method. And finally, I will also show you two Diophantine application of our results. So let me start with the quick review on the modular method. So as I said, I will focus on the case of Fermat's law theorem, because this is on this equation that the modular method was used for the first time. And so to fix notation, I will take P to be a prime greater than or equal to 5. And so the whole proof of Fermat's law theorem is by contradiction. So I'm assuming that there exist non-zero comprised integers A, B, and C, satisfying that A to the P plus B to the P equals C to the P. So there will be 5 steps in the modular method. And the first step is, I call it the construction step. It's mainly due to Elguash and Fry, and it consists in the following. So first you start with your solution A, B, and C, and you consider the following cubic equation: y squared equals x minus AP times x plus b to the p. And so you compute the discriminant of this cubic equation, and it turns out that this is some power of 2 times the product ABC raised to the 2p. So in particular, it's because we're assuming that A, B, and C are non-zero. It's a non-zero integer, and so this equation defines an elliptic curve over Q. And you can already notice from the equation itself that it has full 2 torsion over Q, because the right-hand side is completely split, factors into linear factors. Okay, so now since we have an elliptic curve, we can look at this group of p torsion points on this elliptic curve, for p being the exponent of the equation I'm considering. And as we all know, this is a 2-dimensional FP vector space. So, and there is a Galois action. There is an action of the absolute Galois group of Q, component by component on the set of p torsion points. So this defines a 2-dimensional representation of the absolute Galois group of Q, with values into the automorphism group of the p torsion, which after choosing a basis, I can identify with the group of 2 by 2 matrices, invertible matrices with coefficients in FP. So that's a really important object that is attached to this equation. It's a 2-dimensional Galois representation. And since it's a continuous homomorphism, it factors through a finite extension of Q. And it turns out, using Tate's theory, that this finite extension of Q is actually unramified outside 2np. That's one of the main features of this equation here. Okay, so that was the first step. The second step, which was the last step, which was proved in the history of the proof of Fermat's law theorem. So that's mainly due to Wiles and Taylor-Wise. So first of all, just by simple arithmetic considerations, we can restrict ourselves to the following case. So without loss of generality, we can assume that A to the P is congruent to -1 mod 4, and that B to the P is congruent to 0 mod 16. That just because you can swap A and B, and one of them has to be even, so you decide that that's going to be B, and P is greater than or equal to 5, so it's even congruent to 0 mod 32. And since A to the P has to be congruent, it's odd, so it has to be congruent to plus or minus 1 mod 4, and you can just multiply the whole solution by -1 if necessary, and you have that without loss of generality, you can assume these congruence relations. And under these congruence relation there, it turns out that E is actually semi-stable everywhere, including at 2. And this was important at the time of Wiles, because Wiles and Taylor-White theorem was saying that every semi-stable elliptic curve over Q is modular. So I'm aware that, of course, that now we know much more about the modularity of elliptic curves over Q, but I would like to stick to the minimal conditions that we need to know to prove the Fermat theorem. So, of course, we can use more advanced results. And later in the talk, we will be discussing more recent result where we don't have necessarily have the best theorem at hand. So that's good to know that even if we don't know the modularity of all elliptic curves over Q, which is by now known, we could solve the Fermat theorem because of the properties of this phi curve. So E over Q is semi-stable. That implies that by the work of Wiles that E over Q is modular. And what does it mean for us that E over Q is modular? So there are several equivalent definitions of this, but let's say that let's say that here we understand it that E, so attached to E is a system of L-adic representation, and that system of L-adic representation coincides with a system of L-adic representation attached to some modular form, cuspidal form, eigenform, and that's the meaning of E over Q being modular. And moreover, we know from a paper of Serre from the 80s that attached to some mod P two-dimensional Galois representation is a triple of parameters, which we call the weight, the level, and the character. And we can compute these parameters for the specific case of this rho bar EP representation. And it turns out that it has weight 2 in the sense of Edix-Servan or Serre, and Serre's conductor 2, which I denote by n of rho bar. That just the fact that the Serre conductor is 2 just is related to the fact that this representation was unramified away from 2 and P, and by definition, the Serre's conductor is just the prime 2P part of the Artin conductor. So it's co-prime 2P by definition. So there is only 2 in the Serre's conductor, and the weight is 2. It's just a computation. Okay. Now the third step is the irreducibility step, and it was proved it follows from result of IISER from the 70s. I will go into more details in a few minutes. And so it says that if you look at this representation, rho bar EP, the representation giving the action of the Galois group on the set of P torsion on E, it's absolutely irreducible. And I won't give too much proofs in this talk, but I wanted to discuss this one because it's a conference on rational points on modular curves, and even though we don't prove anything on modular curves in our work, we are using results on modular curves, and this is one step where we use results on modular curves. So let me just sketch quickly the proof of this irreducibility statement here. So assume for a contradiction that this representation rho bar EP is reducible. So if you write D for a rational subgroup of order P and chi for the corresponding isogenic character, I'm trying to stick to the notation that was used yesterday in Barinder's talk. So using the semi-stability of the curve that we have discussed before, it turns out that if you look at the isogenic character will be either the cyclotomic mod P character, chi P, or it will be trivial. That follows from Serre's study of local representation attached to elliptic curves from the early 70s. So if you remember the notation in Barinder's talk from yesterday, what it says is that if you take the 12th power of the isogenic character, it will be either the exponent will be either 0 or 12, one of the two extreme cases that was discussed. So in the case where where the isogenic character is trivial, then it means that E has a rational point of order P. And now remember that E also has full two torsion over Q. So that implies that the group of P torsion points, the group of the torsion subgroup, sorry, has order at least 4P, which is greater than or equal to 20. But remember from Mazur's theorem on torsion on elliptic curves, the maximal order of the torsion subgroup of an elliptic curve over Q is 16. So you get a contradiction there. And in the former case, where the isogenic character is the mod P cyclotomic character, then you just consider the elliptic curve E dash, which is given by E mod D, and this will swap the two characters on the diagonal. So before it was the cyclotomic and the trivial, and now it will be the trivial and the cyclotomic, trivial on the upper left entry. So you get that this curve E dash has a rational point of order P, and you conclude as before. So this is one. I just wanted to point out that there are modular curves in this work. Okay. Fourth step, the level lowering step. So that's due to Ribet, and Ribet theorem has two assumptions. The first is that you have to consider an irreducible representation that follows from the previous step, step 3, and it has to correspond to a modular form. So, and that follows from step 2, when we have proved that E over Q is modular. That implies that in particular, the mod P representation itself is modular. And then Ribet level lowering theorem says that you can lower the level to the cell level of the representation itself. And remember that this cell level was just 2. And when I say that the mod P representation arises from a new form of weight 2 and level 2, I just mean that this representation rho bar, EP, is isomorphic to the mod P representation attached to some new form, F, of the corresponding weight and level. So, but in that case, the parameter, the weight will be 2 and the level will be 2 as well. And there is a final step, the fifth step, which I call the contradiction step. And that just says that we have reached a contradiction because we know that this mod P representation arises from a new form of weight 2 and level 2, but it's a basic fact in the theory of modular forms that there are no such forms, right? So it's a very simple step, because here we just say there is no such form, so there is an obvious contradiction. Okay, so just to recap, so here are the 5 steps in the modular method: construction, modularity, irreducibility, level lowering, and contradiction. So in the rest of the talk, I would like to discuss some extension of this modular method to some other Diophantine problems. And you will see that in the case of the Diophantine problem I'm interested in, we will be able to deal with the first 4 steps in almost full generality, say. But the last step, which was by far the simplest steps in the case of Fermat's theorem, will turn out to be actually the most complicated step. And we will only be able to deal with it in very few particular cases, which in particular in a finite number of cases, depending on the parameters that will be involved. Okay. Feel free to stop me if you have any question. If not, I will discuss now. So I will go to my second part, the extension of Darmon's program, and discuss the precise Diophantine problem I will be interested in. So let's say that we would like to extend this method to some more general Diophantine equation of Fermat type. And those equations are equations of the shape A times x to the r plus b times y to the q equals c times z to the p, where a, b, and c are just fixed non-zero coprime integers, and p, q, r are non-negative integers. So this would be great, and it's actually the goal of Darmon's program. I will be talking in more detail in a few minutes to try to attack these kind of equations using modular methods. But it's quite an ambitious program, and for this talk I will actually restrict myself to a more specific case, which is already hard enough, and namely the case where the coefficient a and b are 1, the exponents r and q are the same, and so that will be the case of equation x to the r plus y to the r equals c times z to the p, where r is going to be a fixed prime, c is also a fixed positive integer, and p is a prime which is allowed to vary. That will be that's a common notation in when we study Fermat equation of general type, that p is always a prime that is allowed to vary, and r and q are fixed. So here there is only r, and I will also use the terminology that rp is the signature of this Fermat equation. And for the equation above, it was rqp. So, but maybe a little more precise in the notation. So r will be a fixed prime number. I will denote by zeta sub r a primitive absolute of unity in C. For every I greater than or equal to 0, I'll denote by omega I delta r raised to the I plus delta r to the minus I. Of course, the omega I is just the Galois conjugate of omega 1, and I will consider h, small h, to be the product of all I from 1 to r minus 1 over 2 of x minus omega I. So that's just the minimal polynomial of omega 1. So it's a polynomial with coefficient in z. And so there so the maximum the R cyclotomic field Q of delta R has a maximal totally real subfield, which I'll denote by Q by K, but remember that K depends on R. So K will be Q adjoint delta R plus, which is the same as Q adjoint omega 1. OK will be the integer ring of K. And so we know that K is only ramified at R. It's unramified away from R, and it's totally ramified at R. So I will denote by PR the unique prime ideal above R and K, and the residue field will be just the field with R elements FR. Okay. So we now have this Diophantine problem that we would like to study. X to the R plus Y to the R equals some constant times D to the P, and we will go through the 5 steps of the modular method that I have recalled just before. So the first step is the construction step. So we would like to attach to put a possible solution to this equation a certain geometric object, right? And so the object that we are considering here is the following. So at this step, I don't really need A and B to be part of a solution, but you can think of A and B being part of a solution to my Diophantine problem. But it's only using the fact that A and B are non-zero coprime integers, such that A to the R plus B to the R is non-zero. So once you have such a pair of integers, you can consider the following hyperelliptic curve, CR of AB, whose equation is given. So you can see it on the slide. It's a bit complicated, but I will show you some example in a few seconds. So you compute the discriminant of this model, and you can see that up to some power of, so up to some sign and some power of 2, power of r, you get A to the R plus B to the R raised to the R minus 1. And since A plus the R plus B to the R is non-zero, you get something which is non-zero, and that equation defines an hyperelliptic curve of genus R minus 1 over 2. So in particular, so I've written down some specific examples to show you that even though the equation seems to be complicated in some specific cases, when you pick a specific value of R, you can easily write down the equation. So for r equal 3, you have this equation, and r equal 3 is the only case where this hyperelliptic curve is actually an elliptic curve, because there r minus 1/2 is just 1. And it turns out that this elliptic curve was used extensively to study the Diophantine, the Fermat equation of signature of 3,3p. But for other values of r greater than or equal to 5, that will be a Abelian variety. If you take the Jacobian of this hyperelliptic curve, that will be an Abelian variety of dimension greater than 1. So not an elliptic curve. So in particular, except for the case where r equals 3, for all the other values of r, which we're not really interested in r equals 3 because it's been studied already, even though it's still open, but it's been studied. So except for r equals 3, we don't have a natural two-dimensional Galois representation attached to this object because the Abelian variety of dimension greater than 1. So that will be the goal in this first step, to construct two-dimensional representation attached to this hyperelliptic curve or Jacobian. And for that, we will use some ideas from Darmon's program. So I have to go now. I will make a short break and forget about my hyperelliptic curve and go to the Darmon's program and recall some definitions and important results. So first notion, which is very important in Darmon's program, is the notion of Frey representations. So for a field M of characteristic 0, I will denote by G sub M the absolute Galois group of M. And here's the definition. It's a definition which is due to Darmon, the definition of a Frey representation. So a Frey representation of signature RQP, where RQP are just positive integers, of a number field L in characteristic L greater than 0, is a Galois representation from the absolute Galois group of the field of function over L of t, with values into GL2 of f, where f is a finite field of characteristic L that satisfies a certain number of conditions, namely these 3 conditions that I have that are displayed. So the first condition is that the restriction to this representation to the absolute Galois group of L bar of t has trivial determinant and is irreducible. So since it has trivial determinant, you can model out the image by the scalar matrices, and you get a representation which is denoted by Robert Guillaume in Darmon's paper from 2000, from the absolute Galois group of L bar of t into PSL2 of f, and you ask for this representation to be unramified outside 0, 1, and infinity. And finally, you want, because I haven't been talking about the signature so far, so now you want that the inertia groups at 0, 1, and infinity map to subgroups of PSL2 of f of order R, Q, and P respectively. So that's one of the key notion in Darmon's program, this notion of Frey representation. And there is also a notion of equivalence between 2 Frey representation. That just means that when you extend the scalars and you go to some algebraic closure of f, 2 Frey representation of same signature will be equivalent when they differ by just twisting by a character. And so there is in Darmon's paper, there is a classification for each signature, each possible signature. There is a classification of Frey representations, a full classification. So I won't give all the results, but I would like to focus on one specific situation, which is the case of constant signature in a sense. So so there is a theorem in Darmon's paper, which Darmon is attributing to Hecke, but which is clearly, which wasn't stated this way in Hecke's work for sure. So let me say it's a theorem of Hecke and Darmon that says the following. So if you pick a prime P, then up to equivalence, there's only one Frey representation of signature PPP, and that representation occurs over Q and in characteristic P. And it turns out that it is associated with the Legendre family, L of t. So it's a family of elliptic curves of Q of t, given by the equation y squared equal x minus 1, x minus t. And since I've been talking about signatures for Fermat equation and signatures for Frey representation, you might wonder whether there is a link between the two, and of course there is some. And it's an easy calculation to check the following, that if you look at the classical Frey-L-Gouache curve that we have introduced before in my quick recap on the modular method, so y squared equals x minus AP, x minus a to the p, x plus b to the p, then you can obtain it after specialization of the Legendre family at T0, which is AP divided by AP plus b to the p, and quadratic twist. So that's the link. So let me just stress the fact that this observation was not needed in the proof of Fermat's law theorem, and indeed Darmon's paper dates back was published in 2000, and whereas the proof of Fermat's theorem dates back to the early 90s. But it will be very important for us later. So remember that this classical Frey-Gouache curve, you can obtain it from a family of elliptic curves over a function field after specialization and twisting. Let me also recall an important definition, which is not due to Darmon, but which is used in Darmon's program. That's the definition of abelian varieties of GL2 type. So if you have an abelian variety over field L of characteristic 0, we should say that it's of GL2 type or GL2 of F type if there is an embedding of a number field F of degree precisely given by the dimension of A into the ring of endomorphism of A over L tensed by Q. And the terminology comes from the fact that when you have an abelian variety of GL2 type, then for each prime ideal in the field F, which I denote by a lambda above some prime L, you can consider the L-dictate module of A and tensor it by the completion at lambda of F, and that gives you a two-dimensional F lambda vector space, and then and there is a Galois action on this vector space, and therefore you get a two-dimensional representation from GL into GL2 of F lambda. And it turns out that these form a strictly compatible system of F integral representation. So we have the same kind of properties that we expect, or that we have for the system of L-adic representation attached to an elliptic curve, for instance. And in particular, you can also conjugate these lambda-adic representation so that they get values into GL2 of the integer ring of F lambda, and then reduce them modulo the prime ideal, the maximal ideal, to get some residual representations. So remember that now. Let me come back to the problem we had before. So let's say we want to attack the Diophantine equation x to the r plus y to the r equals some integer times z to the p. And so you take a solution. You consider this hyperelliptic curve CR of AB. I didn't mention that this hyperelliptic curve was constructed by Cross in the early 90s. And so you consider these hyperelliptic curves, and we wanted to attach two-dimensional Galois representation to it. And so here's the theorem that we've proved with Chen, Diolefay, and Freitas. We proved that there exists a hyperelliptic curve, which I denote by CR dash of t over K of t. Remember that K is the maximal total real subfield of Q of theta R, of genus R minus 1 over 2, with the property that if I denote by GR dash of t is Jacobian, then this abelian variety, which has dimension R minus 1 over 2, is of GL2 of K type, by which I mean that there is an embedding of K into the endomorphism of this abelian variety. And moreover, so this embedding is well defined after specialization. And if you look at for every prime ideal P, frac P in OK, above a rational prime P, if you look at the mod P representation attached to GR dash of T, then it's a representation, it's a Frey representation of signature RRP. And exactly as before, where we have seen that the classical Frey curve was obtained after specialization and twisting from a family of elliptic curves over a function field, our Frey hyperelliptic curve constructed by Cross, CR of AB, is obtained from that hyperelliptic curve over function field after specialization and quadratic twist. So that's an explicit construction, and this construction is actually based on some Darmon's construction, but a little bit surprisingly, it was based on not on the Darmon's construction for signature RRP, but on Darmon's construction for signature PPR. And you will see in a minute that we actually, in our study of Fermat equation of signature RRP, we actually mix results from Darmon's program for signature PPR and signature PPP and signature RRP as well. So all three signatures, if you want. Okay, so now that we have an abelian variety of GL2 type, we can attach two-dimensional Galois representation, p-adic and mod P representation to it. So I will denote by J sub R the Jacobian of the hyperelliptic curve CR of AB, base change to K, because it's over K that it gets GL2 type. And so there is a compatible system of K rational Galois representation attached to JR, which this system is being indexed by the prime ideals in OK. And for each specialization, and that's for all prime ideals in OK. So in particular, we can pick the unique prime ideal in OK above R. Remember that R is ramified in K. It's even totally ramified. So if we pick that specific prime ideal, we get a representation after reduction, rho bar, so GRPR, which by the third point in the previous theorem turns out to be a representation, a Frey representation of signature RRR. So a constant signature, if you want. And that's going to be very important. So that's the end of the first step. We'll go now to the next step, but that will be very important to this specific representation will be very important. In Darmon's paper, it's described as a seed for propagating modularity, for instance. Okay, so the second step is to prove modularity. So we would like to show that JR, abelian variety over K, is modular. And this will be done using the properties, the very specific properties of this particular representation, rho bar JR frac PR. And here's the main theorem. So we assume that R is greater than or equal to 5. And so what we prove is that the representation rho bar, let me just say rho bar for that specific representation, rho bar JR frac PR, from JK into GL2 of FR is absolutely irreducible when we restrict it to the absolute Galois group of the cyclotomic field. So I won't give the full details of the proof, but again, since this is one place where we're using properties of modular curve, I would like to just give you a quick sketch of the proof. And for simplicity, I will assume that R is 11 or greater than or equal to 17, but the proof holds for any R greater than or equal to 5. So first of all, by this classification theorem of Hecke and Darmon, what we get is that our representation rho bar is isomorphic up to twisting by a character of GK to the representation we obtain from the specialization of the Legendre family, because remember that up to equivalence there is only one Frey representation of signature RRR, and that representation rises from the Legendre family. So we have this isomorphism there. So in other words, if we want to study the irreducibility of Robara, we can switch to the study of the irreducibility of the mod R representation attached to some elliptic curve over K. But actually, this elliptic curve L is just the specialization of the Legendre family at some rational point. So it's actually defined over Q. So it's much more easier to deal with, because we know a lot about images of Galois representation attached to elliptic curves. So in particular, we know that the determinant has to be the cyclotomic character, and so the image of for this specific elliptic curve L over Q, the image of the Galois group, the absolute Galois group of the R cyclotomic field, is just the intersection of the image of the whole Galois group GQ with SL2 of FR. And now remember also that L is actually a quadratic twist of the classical Frey-Gouache curve, as I said before. And these curves has semi-stable reduction at R. So by these, again, by the result of Serre from the early 70s, we know that if the image of these the Galois representation attached to the classical Frey-Gouache curve is not the whole group GL2 of FR, then it has to be contained either in the Borel subgroup or in the normalizer of Cartan subgroup. In the former case, we get a rational point on y naught of 2R, and then a contradiction by result of Mazur and Kenku that were recalled yesterday by Ender, for instance. And in the latter case, when the image is contained in the normalizer of a Cartan subgroup, then so this Cartan subgroup can be either split or non-split. And in the split case, from results by Mazur, Momose, and Merel, we know that the J invariant of L dash, and hence the J invariant of L, has to be an integer. And similarly, in the case of non-split Cartan subgroups, then again, by result of Darmon, Merel, and then generalization of them by Lemos, we get again that this is an integer, and we conclude from this. So I'm skipping some details, but let's say these are the main steps in the proof. So now, why are we interested in this result? It's because it's an assumption in a very general recent modularity lifting theorem of Carré and Thorne. And so we can, using these and Serre's modularity conjecture, which is now a theorem of Carré, Vanton-Berger, and Dieu-le-Fait, that the abelian variety of JR over K is modular. So let me just quickly tell you orally how the proof works. So basically, your representation rho bara of JR PR will actually extend to a representation of GQ. That's because JR is just a base change of a Jacobian of a hyperelliptic curve defined over Q, and you will extend it to GQ, and then since it's irreducible when restricted to the Galois group of the R cyclotomic field, it has to be irreducible already over Q. And so you apply Serre's conjecture, you get that it's modular, then you base change it to K, and cyclic base change, it's still modular. And now that you know that the mod PR representation is modular, you get that you have a R-adic lift, which is modular, and from the compatibility of the system, you get that the whole system is modular, and that's how you prove that the abelian variety JR over K is modular. So now we have finished the second step. So first step and second step were achieved for arbitrary values of R. The third step is a bit more complicated, and it consists in proving the absolute irreducibility of the mod P representation attached to JR. But here P will be a prime ideal above the prime P, which is the exponent of the right-hand side, right? And for that step, we don't have a full general result. We only have partial result, but we are able to deal with infinitely many values of R, for instance. And this is one of the theorem we proved. So if you assume some two added conditions, namely that A is congruent to 0 mod 2, so A is even, and B is congruent to 1 mod 4, which you remember we had this same kind of arithmetic assumption in the case of Fermat theorem to guarantee, for instance, that the curve E, the classical Frey-Gauge curve was semi-stable. So this is again some arithmetic condition that we have to impose here, and assume further that R doesn't divide the cardinality, the order of the multiplicative group of the residue field at some prime ideal above 2 in K. Then we can prove, for instance, that this representation rho bar JRP is absolutely irreducible. And how does it work? Actually, under these two assumptions, what we are able to prove is that the representation is already irreducible locally at 2. And so we get that it has to be irreducible. And there are other situations, several other situations where we can prove irreducibility. For instance, for R equals 7. R equals 7 doesn't satisfy the second assumption of this theorem, but still we can prove irreducibility as well. But unfortunately, we do not know how to prove it in general. But I'm pretty confident that if you have a specific values of R, then we can certainly show that it's absolutely irreducible. But we will still have to assume that A and B satisfy these arithmetic conditions. Okay, so let's switch to the fourth step. So the fourth step is level lowering. So it was Ribet's theorem in the case of Fermat's theorem. And so now, if I want to do level lowering, now I definitely have to assume that A and B are part of a solution. So let's say I will assume from now on that there exists a non-zero integer C with the property that A to the R plus B to the R is equal to some constant, capital C, times C to the P. And again, I will assume that I have this arithmetic condition that A is even and B is congruent to 1 mod 4. But here, contrary to the case of Fermat theorem, you have to know that this is a restricted assumption. It's not without of generality. So that's one of the drawbacks of this approach using hyperelliptic curves, that we have to have this arithmetic condition to be satisfied, and that's clearly not the general case. Okay, so but still, assuming this, if frac P is a prime ideal above a rational prime P in OK, the rational prime P being the exponent first, if we assume that we have shown that the mod P representation attached to JR is absolutely irreducible, which we can show in many cases, like in the case where R equals 7, for instance, or R equals 11, then it turns out that there exists a Hilbert new form of a K of parallel weight 2. So Hilbert new form, not just generalization of classical new forms when we work over totally real field. So remember that K is the maximum totally real field in the R cyclotomic field. So weight 2, trivial character, and level, which is given by 2 to the 2 PR squared, and the product of all prime ideals in K, which are co-prime to 2R, and that divides C, the C being the coefficient in front of the piece power on the right hand side, such that we get an isomorphism again between the mod P representation attached to JR and the mod P for a capital frac P in the coefficient field of G. So the representation attached to G and this prime ideal. And moreover, what we can show, and this will turn out to be very important in the practical the practical cases I will discuss later. Moreover, we have that the coefficient field of G has to contain the field K. And this theorem follows from first a refined level lowering theorem of Bryan Diamond, and a precise description of the image of inertia, and in particular at the prime ideals above 2 in K. So we are now done with the first 4 steps in the modular method, and except for the case of irreducibility, the step of irreducibility, all of these steps were achieved in rather full generality, right? Except, so we have to restrict, maybe we have to be careful in the case of irreducibility for specific values of R. There might be some issue there, and that we have to impose some arithmetic condition here to make sure that we can prove everything, right? So that's a bit restrictive, but still we can deal with almost arbitrary values of R. Now remember, I'm now turning to my last part in the talk. And so now we'd like to discuss the last step, the elimination step, which was, remember, the easiest steps in Fermat's theorem. But here there are many problems actually, because, and that's often the case when we deal with generalization of Fermat's theorem to Fermat type equation of different signatures, that we end up working in a space of modular form, which is non-trivial, right? And so we are facing the problem of discarding this isomorphism that I have here. And there are several issues with this last step, and actually the main 2 issues is that first, Newform subspaces that we have to consider may not be accessible to computer softwares, either because they're too large or by lack of efficient algorithms, for instance, in certain cases, depending on the type of the level. It could be, it's not only the size of the level, but also the type of the level that can be a problem to compute the space of modular forms. And also because we miss a general method to discard an isomorphism of the shape rho bar, an isomorphism between the mod P rotation attached to some abelian variety and the mod P rotation attached to a Hilbert Newform. And you might think already on the how do you discard an isomorphism between the P torsion group, the mod P rotation attached to 2 elliptic curves of a Q. It's really difficult, right? If they look too similar, you don't know how to discard it. So these are the 2 issues that we are facing now. And what I would like to explain in the last 10 minutes is 2 specific cases, 2 specific Diophantine equations where we have been able, at least partially, to solve these problems. So the first case I would like to discuss is the case R equals 7 and the coefficient in front of the piece power being 3. So here the theorem from last year. For every integer n greater than or equal to 2, there are no integers a and b and a, b, c, such that a to the 7 plus b to the 7 equals 3 times c to the n, where a, b, c are non-zero and co-prime. So for the proof of that theorem, we are actually using what we call a multifry approach, after terminology which was introduced by Samuel Sixek and Bijot and Bignot. And so multifry approach means that we are going to use several fry objects. And in this specific case, there will be 3. So first, we will be using a fry curve of a Q, whose construction is due to Darmon. I have displayed here the equations, not really important, but you can see it's quite explicit. So there will be this elliptic curve of a Q. There is another elliptic curve, which is this time defined over the field I have I denoted K before, but which is just the maximum to the real subfield of Q zeta 7 here, because here R is 7. So it's a cubic field, totally real cubic field. And so again, you have the equation here. So it looks similar. It's similar to the classical Frey curve, but it's defined over K, over a number field. And finally, we will be using the Frey hyperelliptic curve of Krauss. The curve C was equation is given by on the slide, and it's Jacobian when we best change it to Q zeta 7 plus. Okay, so that's the first thing. We are using these three objects. Of course, we are also doing some computation, and these computations are done using magma because we have to compute in modular form spaces. So in particular, when we deal with F, which is an elliptic curve over K, and J, which is the Jacobian of this hyperelliptic curve, and Jacobian over K. And that gives us three different proofs of this result. So I have here, you can see the three tables will indicate. So in each table, for every 2-adic and 7-adic possible conditions that might be satisfied by a solution, I have noticed, I've indicated the Frey object that we are using. So the first proof in the table on the left upper corner here is using only elliptic curves, as you can see. It's using E. Is actually not quite necessary, but it's somehow easier from a theoretical point of view because it's using only modularity of a Q, classical forms, not Hilbert forms. So somehow it's satisfying when we have an elliptic curve of Q, but it's not sufficient. He only allows you to deal with these cases where 2 is odd and 7 doesn't divide A plus B, or when 2 divides exactly once AB and 7 doesn't divide A plus B, or in that case here where 7 divides A plus B and 4 divides AB. For the other cases, we need to use F and some quadratic twist of F. So F within bracket -7 means the quadratic twist by -7 of F, and so on. So if we use a mix of these elliptic curve here, we have a proof which is using only elliptic curves. Now we can also use the abelian variety, the 3-dimensional abelian variety J, of course, and all the techniques that I've been discussing before to give a proof of this theorem in the case where 2 is even. Sorry, 2 is always even. In the case where AB is even. In the case where AB is even, then we can use only J. So this is a proof where we use J as much as possible. And finally, we can give a third proof of that theorem where we use a more balanced mix of elliptic curves and abelian variety of dimension greater than 1. So namely, we use E or F in all these cases. And in the last two cases where 7 divides A plus B and 2 divides AB, we use J. And now we can compare these two approaches. And so we use a multiply approach using the 3 Frey objects. We use computation, and we have 3 different proofs. And the first proof that was using only elliptic curves takes 41 minutes using magma. The second proof, which is using F and J as much as possible, takes 8 minutes. And the third proof, which is using a more balanced mix of elliptic curves and abelian variety of dimension greater than 1, takes only 1 minute. And that's a bit surprising. And you can notice that the proofs that using the hyperelliptic curve C are actually faster. And the reason is that we have developed techniques, efficient techniques to discard the isomorphism between the mod PR representation attached to J and the mod P rotation attached to J and the mod P rotation attached to Hilbert new form. And these techniques are really deeply relying on the condition that I've mentioned here, that the field of coefficient of the modular form that we are considering has to contain K. And that turns out to be a tool which is only available in the case where you have abelian variety of dimension greater than 1, not the elliptic curve, and which turns out to be very efficient. So if you're lucky enough, the computation of the initialization of the space is quick, and using these conditions, you can perform the elimination step very quickly, and that's why you get very fast proofs. But it's still, you might say, okay, it's just a matter of time, and then you can still wait 41 minutes and you get a proof without using hyperelliptic curve. So I want to show you another Diophantine application of the result I've been talking about today, where abelian varieties of dimension greater than 1 are really necessary. So here the result, again from last year, for every integer n greater than or equal to 2, there are no integers a and b and c, satisfying that a to the 11 plus b to the 11 is c to the n, where a, b, c are non-zero co-prime, and satisfy these 2 and 11 adic conditions here. And again, so if you want to attack this kind of Diophantine problems, we will be using a multi-Fry approach. This time, with only one, there is only one Fry elliptic curve which is available in the literature, and its construction is due to Freitas, and it's an elliptic curve defined over the maximal totally real subfield of Q zeta 11, and it's a degree 5 extension of Q. And again, we're going to use also the Fry hyperelliptic curve across C11 and its Jacobian base change to K. And there, the total running time in Magma for the elimination step is 7 hours, which are split in 6 hours for the computation of the initialization of the relevant Hilbert space that we have to work with, and 1 hour to perform the elimination. And maybe it could be a little smaller, because the elimination is, as I said, using the techniques we have developed, the elimination can be really quick. But now, if you want to prove this result using only property of elliptic curves, you don't want to use Fry abelian variety of dimension greater than 1, then it would require to do computation in the space of Hilbert new forms of level p to the cube times p11. So where p2 and p11 are the only prime ideals in Q zeta 11 plus above 2 and 11 respectively. And that space of new forms has dimension 12,013, and it's not currently feasible to compute with it. So there's no way you can, at least from now, using the current technology in terms of computation of modular forms, there is no way you can prove these results using only elliptic curves. You have to go to Fry abelian varieties of dimension greater than 1. Okay, thank you. I'll stop here.
Questions?
Hello. Yeah, thank you. Nice talk. So I have one question. In the extension of Darmon program, so when you construct this Jacobian JR, so there have you proved this semi-stable of JR at primes away from 2?
How do I prove what? Sorry.
Semi-stability of JR away from 2.
Oh,
like you prove modularity and irreducibility level lowering. I am just asking about the semi-stable part.
So first of all, the construction of these hyperelliptic curve over the function field is quite explicit. So we have explicit expression of the coefficient and so on. And so to study the reduction type at every prime, actually, even at prime. So there are different, of course, there are several cases to consider. So the prime ideas above 2, prime ideas above R, so PR, prime ideal dividing A to the R plus B to the R, and those that do not divide this. And in each case, we are studying we are just working with the explicit models and making change of variables to study the reduction type. The problem is that in the case where AB is odd, we're stuck because, first of all, it's not clear with what type of reduction we have, and also by studying the reduction type, we are able to pin down the exact type of the local representation. So, for instance, you know that when you restrict to a prime ideal above 2, the local representation will be either principal series or special representation of or supercuspidal one, or even the exceptional one, say, in the case where P is 2. And we are able to, from the information we get from the reduction, we're able to say, okay, in that situation that will be a principal series, or in that situation that will be a supercuspidal representation, and induction of an irreducible representation, for instance. And that's how we get not only the conductor but also the irreducibility, because if you know that the mod PR representation is irreducible when restricted to a decomposition group at 2, then it has to be reducible globally. So it's just explicit computation with models.
So in this case, we don't require this semi-stability part.
No.
Okay, thank you.
No, yeah. No.
Thank you.
Nicolas, it's Samuel. Can you hear me?
Nice. Yeah.
Thanks for the talk. I had well, I guess very vague question. You explained at first that for a Darmon program in signature PPP, basically you have only one possibility.
Yes.
Right? Do you have an idea of what's going on here with signature RRP, especially because with multifry, it looks like you have several possibilities.
So there is a full classification of Fry representation for each signature in Darmon's paper. So there are some odd and even Fry representations, and Darmon is classifying all of them for each signature. The thing is that his construction for the case of signature RRP is using super elliptic curves, which are not really easy to deal with in practice. And since we had these Fry hyperelliptic curves that were constructed by Cross, we somehow wanted to make them fit into the Darmon's program. So and we found that actually they somehow come from Darmon's construction for the equation the signature PPR. So in signature PPR, so a priori there is no relation between because there is no way to prove that a Fermat equation of signature RRP, the 3,3P, for instance, has no solution because another Fermat equation of signature P33 has no solution, right? But there turned out to be a surprising link between Darmon's construction in signature PPR, and so we could just use this construction that was using hyperelliptic curves to show that Krauss hyperelliptic curve arise by specialization and twisting from just a modification of these constructions in signature PPR. So it's a bit surprising that, but that's how it works. But in any case, we if you're interested in, so I don't know exactly. So I guess your question is whether our constructions give new Frey representation of signature RRP, for instance. They don't give any new representation. They must fit into the Darmon's classification, and I'm pretty sure that they don't give the full classification. But it's just another way to construct this Frey representation of signature RRP.
Okay, thanks. I have another small one, if that's possible. Why? So it's for the equation with the powers 7. So it's A7 plus B7 is equal to 3CN, if I'm correct.
Yes.
Is it actually harder to try to do it without the coefficient 3?
Yes, because of trivial solutions.
Oh, okay. But you don't have them in
one of the main obstructions in solving Diophantine equation. So we wanted to. So you have to be careful, because if you don't put coefficients in front of this, you might run into trouble because of the trivial solution. And there is no way you can discard an isomorphism after level lowering if you have a trivial solution that gives you an object with the right properties, right? So the thing is, in the classical Fermat theorem, trivial solutions that give rise to singular curves, so they are just discarded immediately. But in other situations, trivial solution might very well give you non-singular objects, right? And in that case, you're always stuck. So of course, by putting a coefficient here, we just avoided dealing with trivial solution. But on the other hand, you have to pay attention, because if you put two coefficient which is too big in front of that, then the problem you will have is that the three that we put here, it appears in the I didn't say which level we have to compute with, but it will show up into the level of the form that you have to consider at the end. And if you put too many coefficients in front of the C to the n, then you might end up having a space of modular form that you cannot compute with because it's too large. So putting coefficients is useful at the beginning that makes your life easier, because you get rid of the trivial solutions that are very embarrassing. But at the very end, you might pay the price because you cannot compute with the space. So 3 was a good choice in this sense. That.
So just to be sure, what would be a trivial solution without the coefficient 3?
The trivial solution would be 1, 0, 1, for instance.
Oh, when you allow 0, okay.
When you allow what?
When you allow 0, because then there could be also trivial 1 here. You take 1 minus 1, 0, for example.
Yes, but 1 minus 1, 0 will give you something singular here.
Okay. Thank you.
There is a question for David. Maybe you can pass the mic.
Hi, Nicolas, it's Davide. But actually, I had a very similar question to Samuel's. So I wanted to ask if you have any conceptual explanation for the fact that you start from something of signature RRP and you end up working with representations of different signatures. But I think you already said you don't have a...
No, I mean, this is not something you can really expect from the beginning, I would say, because again, at the level of the Diophantine equation, you don't see any relation between signature RRP and signature PPR, for instance. But it's at the level of this classification of Frey representation over representation of absolute Galois group of function fields that you see some relation. So it's a bit surprising, and also the fact that we are using constant signature, so RRR, PPR, PPP. It's less surprising because it was already in Darmon's paper. He was saying that these specific representation should play a specific role in propagating modularity in the whole system and so on. But still, we didn't expect this from the very beginning.
Any other question? So then we can thank Nicolas again.